these last number of talks after Sophie's operations talk are more closely related to Earth. So we have ionosphere and magnetospheres for the rest of the day, before we have the student talks, or after we have the student talks, and then future perspectives. But now Laura Hayes is going to talk to us about ionosphere. Yeah, okay, over to you, Laura.
Yep, great. I'm assuming you can see my screen. Yeah.
Sure thing. Yeah. All good.
Cool. Okay, so hey everyone. Yeah. So what I'm going to talk about today is the Earth's ionosphere, and particularly space weather impacts, but really more about solar flare impacts. So kind of building on a lot of what Sophie talked about. So a little bit of a disclaimer, I'm not an ionospheric physicist. I'm still learning myself. I'm a solar physicist. I study solar flares, and this is how I kind of got interested in the ionosphere. It was really like studying solar flares and seeing their impacts on Earth and how we can kind of use different observations of kind of Earth-based measurements of the ionosphere to see how solar flares impact it. So what I'm going to talk a bit about today is here's just a little overview. It's going to be quite a high-level talk of, you know, what is the ionosphere, kind of an introduction to it. I'll talk about the different regions of the ionosphere, the D, E, and F region, their different characteristics and how they're all differently impacted by solar flares and how we can probe them. I'll talk about, again, the space weather impacts of these different regions and how those adverse effects can happen. I'll talk about how you can probe these different regions, because again, they have different characteristics, so different ways we have to look at them. And then kind of finish with some questions of what we still don't know and where we are in the field and what we can do to really kind of further our understanding of kind of the Earth's ionosphere and its impacts that it kind of gets by large space weather events, in particular solar flares. So just to begin, for those of you who aren't aware, the Earth's ionosphere is the ionized portion of the Earth's atmosphere. So similarly, other planets have an ionosphere, depending on the atmospheric components, and of course, it's driven by the sun. In terms of our own ionosphere, it is around 60 kilometers in altitude above kind of sea level, up to around 1,000 kilometers. And again, it is directly linked to solar output. It is created by the sun. Solar EUV emission ionize the kind of the neutral composition of the atmosphere of the Earth, and this causes a lot of free electrons, and then you have essentially a plasma. So you have free electrons floating around and you have this ionized portion of the atmosphere. And again, it's divided, as I mentioned, into these three layers. And these three layers, it's split up onto based on its electron density profile. So it's not just a linear gradient of electron density increase in the ionosphere. It actually has these little bumps and wiggles, which we'll talk a little bit about. And in terms of where the ionosphere lies in relation to the atmosphere, we can see the D region is the lowest lying region. We have the E region and the F region. And again, I'll talk about a little bit more about these in detail. But just to kind of give some reference of the ionosphere in respect to the atmosphere, this is a nice kind of plot to show that. So we can see the levels of the atmosphere if we go up above sea level. We have the troposphere, the stratosphere, the mesosphere, the thermosphere. And then when you go up, you have the exosphere into space. And the ionosphere is really the boundary between space and kind of Earth and terrestrial weather. So to give you an idea, the ionosphere really only goes up to, the base of the mesosphere up into the thermosphere. So you hear an awful lot about the ionosphere-thermosphere coupling, and that there's an awful lot of intricate chemistry that goes on there. But just again, to give you kind of some perspective, like all weather and everything like that is down in the troposphere, so quite low down, or up to around 10 kilometers. The stratosphere, this is where you have the ozone layer. The mesosphere, this is where meteors get burnt up and things like that. In terms of where things lie in space, here's a picture of the space shuttle. The International Space Station is around 400 kilometers up in altitude. And this kind of hosts, again, the ionosphere hosts all kind of satellites that are propagating or orbiting Earth. So this is just to give you an idea of kind of where we are in space and the space we're kind of talking about when we go up in the atmosphere of the Earth. And another thing to note is as you kind of go up in altitude, the neutral density decreases, right? So it's much more dense down here in terms of neutral density than it is up here. And that's important when we go to think about the ionosphere. And then going back and kind of looking at these individual layers of the ionosphere, I said that these layers are defined based on the electron density structure. So if we go and have a look at this plot, this is looking at altitude versus the electron density. And we can see the profile, and we can see straight off from this plot how how it is so directly linked to the sun's output. We have both here profiles during the night and the day. So obviously on the night side ionosphere, the sun isn't present, it isn't as much ionizing the neutral components of the atmosphere, but it's still kind of there. And we also see a difference between solar minimum and solar maximum. And this is due to the fact that, say, in solar maximum, you have an awful lot more EUV, extreme ultraviolet emission coming from the sun. Now, if we go and look at these little profiles, we can see that these bumps essentially are what define the different regions of the ionosphere. We can see the lowest lying region, the D region, is very low in electron density relative to the upper region of the ionosphere. And we can see that the D region almost disappears completely at nighttime. As we move upwards in altitude, we can see the E region. So this is the next region, and it's defined by this other little bump. And we can see at nighttime, it does significantly decrease, but we still do have this, this bump in the electron density profile. And then we have the F region. This is kind of the dominant region really of the ionosphere in terms of free electrons. It's orders of magnitude higher than the D region. And during the day, we actually find that the F region breaks into an F1 and F2 portions. But at nighttime, it really does still exist. So we have an ionosphere throughout the nighttime as well. It just gets significantly decreased, much lower in the altitude. Now, why we care about the ionosphere and why it's becoming more and more important to understand it really is that the ionosphere plays a governing role in essentially all radio communications. So this includes, a satellite talking to GPS receivers or to any satellites. It has to propagate through this ionized medium. So if we heard, radio wave propagation is, of course, depends on the medium it's traveling through. We had the talk yesterday, Richard Fallows, talking about ionospheric scintillation and things like that. So, if there is any disruption in this ionosphere, it's going to impact how these radio waves are propagated. And similarly, as well as trans-ionospheric propagation, so going out into space, we have to also think about sub-ionospheric communications and transmission. So radio waves such as high-frequency communications, which is around 3 to 30 megahertz, propagate globally by bouncing off essentially the F region of the ionosphere. So you have a signal that passes up, and it reflects and it propagates around large distances around the globe. And similarly, from an observational perspective, if we're looking at things in space, if we're looking at radio emission from the sun, this radio emission, of course, then has to get back through the ionosphere for us to be able to observe it. So you have kind of this two-way system of trying to understand it. And this goes back to the idea of, we talked a lot about, this ionosphere cut off at around 10 megahertz where you can't see radio observations below that, and that's because of the ionosphere. Essentially, you have the opposite thing happening, that those radio waves are going to be reflected back outwards. And I guess looking at the critical frequency at which a radio wave will reflect, we've seen this equation a lot this week. This is the critical frequency, so the plasma frequency essentially, and it's related to the electron density. So if you think about it, the higher the electron density, the higher the critical frequency. So you can have higher frequencies then can go to higher regions of the ionosphere, and then some of them can obviously pass through because the electron density in the ionosphere isn't high enough. So just something, this is an equation that we really need to keep in mind as we kind of go forward in this talk. So it's really important to why we care about solar flare effects on the Earth's ionosphere. So moving on now, what I'm going to just go into is a little bit of a deep dive into each of these individual layers and their different characteristics. So to begin, the F region, which is the uppermost region of the Earth's ionosphere, it extends in terms of altitude from approximately 170 kilometers up to around 600 kilometers. And then above this is called the topside ionosphere. And this is where the magnetic field, the Earth's magnetic field really dominates. As I mentioned, during the day, it's split into two regions. So we have two little bumps again. So the F1 region, which is 170 to 200 kilometers in altitude, and the F2 region, which is 300 to 600 kilometers. And again, at nighttime, it really just, these kind of go back just to be, just call it the F region. In terms of what causes it, it's really dominated by UV and EUV emission in the range of around 100 to 1,000 angstrom from the sun. So these emissions from the sun and these wavelength ranges, these ionize atomic oxygen in this region of the ionosphere. And that's why it's so dominant. There's an awful lot of atomic oxygen at those altitudes, and you have an awful lot of EUV and UV emission in that wavelength range. So that's what creates the F region. Why it is so important is that it does facilitate high frequency radio communications. And there's kind of this idea here where you have a transmitter, it emits kind of high frequency radio waves, and these these waves are at frequencies that reflect in the F regions really nicely, and again can propagate at large distances. And high frequency radio communications are still widely used by many different industries, so they're really important, and we really want to have an understanding, I guess, of the conditions of the F region and how then it's going to change.
Laura, can I ask just, I can never remember the radio distinctions. HF, high frequency communication, what frequencies are they?
So that's at 3 to 30 megahertz.
3 to 30, okay, yeah.
Sorry, I should have put that in there. Yeah. So that's kind of what we would say the band of high frequency communications is.
Okay.
Which we call low frequency zone.
We call it low frequency.
Yeah. Yeah, this is one of the problems between the different disciplines. But yeah, 3 to 30 megahertz is what you need to think about. And I guess they can propagate because they're not going radially up; they're going at an angle, which allows them then to bounce essentially or reflect. But yeah, it's a good question. And I guess in terms of other characteristics of the F region, it has a very high electron density, and this is due to the fact that the neutral density of the atmosphere is so low here. So again, as we go upwards in altitude, the density of the air, the atmosphere decreases. So essentially, when you have ionization, it's hard to then recombine because there's not enough essentially neutral atoms to be able to recombine into. And this is why the F region essentially exists at nighttime. It just takes so long for things to recombine that by the time it starts to recombine, the sun is coming back up again. So yes, that's the F region. And again, if you want to just think about the F region, it's the dominant one that has the highest electron density and the one that's important for high frequency radio communications. Now moving down into the E region, which is the next region, this was actually the region first discovered by Marconi back in the 1900s. In terms of altitude, it's around 100 to 170 kilometers upward. In terms of what causes it or what its dominant ionization is, this is due to kind of EUV and soft X-ray wavelengths and around 10 to 100 angstrom, but then also in kind of the UV, so 1,000 to 1,500 angstrom. And in terms of what it ionizes, what components it ionizes, it actually ionizes molecular O2 rather than atomic O2. And this is what causes the E region. Again, it does reduce at nighttime, but it's still present. This is an important region because it kind of hosts the ionospheric currents. So if you've heard like the polar electrojets or the equatorial electrojets or the solar quiet currents, these all occur in the E region around that altitude. And this is important for things like geomagnetic storms and things like that, that we can see them then in magnetometer data, which I'll talk a little bit about later. You can also have this thing called the sporadic E region, which are kind of like blobs essentially of regions of high electron density that can propagate around at this altitude. And I mean, what causes them is still quite unknown. They are thought to be caused by, space weather effects, whether that be a flare or whether it be kind of like an energetic particle event. And why they're kind of interesting is that their electron density can be so high that it actually is similar to what the F region electron density is. So you can get sporadic times where if you're using reflecting, frequencies used to reflect the F region, they reflect the E region, then you get huge phase shifts because your wave is reflecting at a much lower altitude. So they are quite sporadic in a sense. They can be quite localized both in space and in time. And I won't talk too much about this because I really don't know too much about this, but just something you might have heard about before as sporadic E region. So that's just what it is, a little blob of high electron density that moves around the E region. And then finally, the D region, and this is the one I'll probably focus on the most throughout this talk. It's the lowest lying region, around 60 to 100 kilometers in altitude. And it's really created during the day. As I said, it mainly disappears at nighttime. It's created during the day by Lyman alpha emissions, so the most dominant emission line from the sun. Look at it, it's the hydrogen line essentially. And this acts on nitric oxide. So the chemistry in the D region is much, much more complicated than the higher up in the atmosphere. And this is due to kind of high neutral density. And you can have an awful lot of like negative ions and things like that. But it's really like nitric oxide, which isn't a major component of the D region, but any of it that is there is ionized by Lyman alpha. And I guess the D region, why it's so interesting and why it's so important from a solar flare perspective is that this is the altitude that X-rays can penetrate down to in the atmosphere. So this is really important during a flare where you have orders of magnitude increase in X-rays. They penetrate down to this lowest lying region. And what they do is they completely ionize oxygen and nitrogen. So nitrogen and oxygen are abundant at this altitude, and it completely dominates ionization. So you've orders of magnitude increase in the electron density in the D region caused by a flare. And this is kind of the stuff that Sophie talked about. This is what causes our high frequency blackouts and things like that, which I'll focus on a little bit in a minute. But just something to keep in mind. Now, compared to the F region that has a very low neutral density, the D region has a very high neutral density. And what this means is that collisions are very dominant, are very frequent. So you have an awful lot of collisions going on, and recombination processes occur very quickly. So this means that if you ionize something, it will recombine very quickly into something else. And this is why you have loads of negative ions and really complicated chemistry that we really don't fully understand just yet. And it is the fact that we have such a high collisional frequency, and the fact that you have these recombination processes dominating, that it really is disturbing to any radio waves that propagate through it. So if you think of things that are reflected higher up in the altitude of the ionosphere, everything has to propagate through the D region. So any radio waves that's propagating through a region that is, say, has kind of high collisional frequency and is more ionized compared to normal, it's going to either absorb your radio wave or at least significantly attenuate it. So it is this lowest lying region that we really need to care about and think about. And why, again, it's important to think about if we go back and think of that plot that showed, you know, the altitude regions and different portions of the atmosphere. The D region is a funny altitude. It's too high for balloons and too high for balloons, and but it's too low for satellites. So there's no real way to directly probe it. And in this way, it's kind of the most least understood. So now what I'm going to move on to is, again, going back to think about solar flare effects on the Earth's ionosphere. So we've some really nice talks this week. We've seen kind of an introduction to space weather events with Sophie's talk, and kind of previous in the week, we've seen about solar flares and coronal mass ejections. And both of these things together are known as a solar eruptive event. And both of these things have a significant impact on the ionosphere. What I'm going to focus on really today is looking at solar flare impacts on the Earth's ionosphere. So just to remind you, the solar flare portion of a solar eruptive event is the intense increase of radiation across the whole electromagnetic spectrum. And the thing to think about again is that when a solar flare occurs, it's already occurred and we see it at Earth. So it's just light. So we don't really have a way to kind of, if we see a CME, we can say, well, it's going to arrive here in a few days or a few hours. But when a flare occurs and we see it, it's already happened and it's already having an impact on the Earth's ionized environment, the ionosphere. So again, just thinking about solar flare, it's driven by magnetic reconnection. You have this rapid release of free magnetic energy. We've seen that this drives essentially emission across the whole electromagnetic spectrum, from radio waves all the way up to gamma rays. So these things, solar flares, can be so bright that if you look at the full disk integrated flux from the sun in, say, EUV or in X-rays, it's going to increase by orders of magnitude. And what this is then going to do is going to increase the solar output by orders of magnitude, which then, of course, is the direct impact on the Earth's ionosphere. And this is just a snapshot. I'm really only looking at the UV portion of the spectrum. This is with timed SEE data. So this is looking at the spectra, so we can see wavelength here in flux. We can see, of course, this is during no flare quiet time. The strongest line is Lyman alpha emission. However, when we have a solar flare, we can see that, again, the output from the sun across the whole wavelength band increases. And just to note, this is a log scale. So this is from an X17 flare, I think it was back in 2003, one of the largest flares that have one of the strongest impacts on the Earth's ionosphere. So we can see that, again, during a flare, this increased radiance across the entire spectrum. But if we actually look at the percentage increase of this flare across the spectrum, we can see it's on the order in the UV range of around 100%. But as you kind of get closer to the EUV or the extreme ultraviolet wavelength range, you can see it goes up to like 1,000%. And as you kind of move down this wavelength band, if you went into the soft X-rays, you would see that it actually increases by, you know, it can be tens of thousands, hundred thousands of percent increase. And again, why this is important is if we go back to this image and—
Sorry, Laura.
Yeah.
Can I ask you a question?
Yeah. Peter, I think you're muted. Sorry.
Sorry, I did that to myself just as I started talking. The bottom plot there, that's the ratio of the red plot of the flaring to the non-flaring.
Yeah.
And how come the Lyman alpha doesn't jump up so much? Does it not? It's hard to see.
The Lyman alpha emission, I mean, the line doesn't increase dramatically over a flare, but I guess the amount of power that would be in this Lyman alpha line would be a lot, because the flux increase is going to be large. But usually with Lyman alpha, you don't see a huge increase compared to the other lines.
Okay, I guess I would have thought that Lyman alpha would have increased, because Lyman alpha comes from the chromosphere, comes from the flare ribbons. I just would have thought that it would, but maybe while integrated over the whole sun, it's not as prevalent.
Yeah, I think that's the point. I think it's that this is a full disk integrated and Lyman alpha line is so bright. I also have to double check this flare. This might have been a limb flare in the sense that it mightn't have been that the Lyman alpha line was optically thick. But usually looking at these things, you don't, compared to the other lines, you don't see as a large an increase. And I think that is, again, just because the Lyman alpha line is so bright.
Okay, thanks.
Yeah. So, yeah, thanks for that question, Peter. So yeah, going back to the idea of increased solar output and how this is going to impact the ionosphere, we have a nice stable ionosphere. It's created during the day to the nice sun. However, when you have this intense brightening over the matter of minutes, what can happen is you have a substantial increase in the electron density, essentially on the entire day side ionosphere. And it is particularly important from a solar flare perspective because it is really the EUV and X-ray emission that increase by orders of magnitude during a flare. And these penetrate down particularly to the D region and to the E region to increase the electron density profiles there. And in a way, what I've tried to highlight in this little cartoon is that any signals then propagating through are going to face a more higher electron density profile. And in this way, they're either going to be refracted, they're going to be attenuated, or in some cases, they're going to be completely absorbed. So this is when you get a high frequency blackout. And you can also have things like ionospheric scintillation effects going from transmitter to receiver, talking to satellites. Communications can be lost. And this is really the space weather impacts of solar flares on the Earth's ionosphere. And what does this look like in terms of ground-based data that's trying to observe the ionosphere and see these different effects in the different regions of the ionosphere? This is, again, Sophie talked about the Carrington event. So this is this large white white light flare that occurred, and it was also associated with a large geomagnetic storm. But if we look at ground-based magnetometer data from the time of that event, this is actually with a self-recording magnetometer, we can see that in the magnetic field at the time of the flare, which is around here, we can see this dip or this little bump in the magnetic field data. So this is kind of the first observation, is what we call a magnetic crochet, which is showing that a solar flare is actually having a significant effect on the magnetic field or the currents in the Earth's ionosphere. In terms of looking at this total electron content, so this is like looking at the total electron content from the ground the whole way up to the upper F region. This can be monitored with GPS observations. So this is, again, looking at kind of the differences in phase. I'll talk a little bit about this in a minute, from receiver to satellites. And you can get an idea then how the total electron content of the ionosphere over the day side ionosphere is affected. And we can see, the flare happened around here, and we can see, this is hard to see on the scale here, but this is the total electron content units. And we can see it's much brighter on the day side ionosphere. And significantly impacted, as we mentioned in what Sophie talked about, we saw a similar plot. This is high frequency radio absorption. So this is the NOAA D region absorption prediction model, which looks at the highest frequency that will be affected. So essentially, if you have a higher the frequency, going back to that idea that the reflection frequency is related to the square root of the electron density, the highest frequency affected is going to be the higher electron density profiles in those D regions. So we can see for this flare, up to, you couldn't really use frequencies up to around 35 megahertz, or if you did, they were definitely attenuated. So we can see this attenuation scale here. And to give kind of a recent example, this is actually the example that Sophie gave of an adverse effect that really impacted, us at Earth, was these two large X-class flares of the past solar cycle, which we've analyzed this week with radio data and X-ray observations and EUV observations. And they significantly disturbed the D region ionosphere. So this is only the X-ray portion of the solar eruptive event. And they really caused radio blackouts for several hours. And I guess why this is important is that, as Sophie mentioned, these two flares occurred at the same time of hurricanes Irma and Jose. And the reason why this is important is that, you know, normal communications were actually down due to the fact that they had these large storms. So emergency responders were really relying on high frequency radio communications. And what they had was essentially they couldn't use any of their communication equipment for over several hours during these two large flares. And similarly, there was a French aviation plane that was a civil aviation plane that was coming to kind of provide help, and they lost communications with that plane for over 90 minutes, as Sophie mentioned. So this is just one recent example of, you know, really adverse effects solar flares can occur on the Earth's ionosphere. And again, just to highlight that, you know, this is why we need better solar prediction or solar flare predictions. You know, when we've seen it's already happened. So we really want to understand, you know, when it's going to happen and how large that flare is going to be, and to try to understand how long the ionosphere is going to be disrupted for. And I know it's hard to mitigate this because if your high frequency radio waves aren't going to work, they're not going to work. But maybe it's a fact of, you know, using a higher frequency or being able to predict when you'll be able to use your communications again in the future. So now I'm going to go through and kind of talk about how we kind of probe different regions of the ionosphere in respect to a solar flare. And the first is looking at this total electron content, which I mentioned in the previous slide. So the total electron content, or the TEC, is an important parameter to explain the effects on radio waves. And essentially what it's defined as is the integral of the electron density along some path. So usually what it's defined as the integral of the electron density from the ground all the way up to the top of the ionosphere. And it's an important parameter because if you think about it, it will tell you essentially how much a radio wave is either going to be refracted. And we can measure the total electron content essentially by using kind of the network of GPS, or the global GNSS satellite network. And this can be done by measuring essentially dual frequency GPS signals. So if we look at the L1 and the L2 bands, that's around 1.2 and 1.5 gigahertz. So essentially the electron density is going to change the kind of phase delays between different frequencies. So if you look at the phase delays between these two signals, you can essentially make an estimate of this total electron content. And this is what's done here. And GPS satellite ground-based receivers can do this on the fly, essentially to correct for it. But then also it gives us kind of a probe to be able to then measure the total electron content and try to understand it. And this is the idea, like, you know, GPS satellites orbit around 20,000 kilometers, and their signal is really impacted then between this, you know, relatively lower region of the ionosphere. So essentially, if you have a large region of electron density, it's going to be refracted out, whereas usually it would go down if the electron density was quite low. And just to kind of highlight here, TEC measurements are really great and really important, and they're really good for during the day, but they're really dominated by the F region. If you're going to integrate the electron density across this whole altitude region, you're not really going to see the D region, it's so low. So this is another reason why it's really, really hard to measure the D region, because the total electron content measurements don't really give you a good estimate of how the electron density in the D region is going to be impacted. So it's really the F region and the E region that TEC measurements can provide you with. And if I just mention a quick thing, and I guess I'm really out of my depth here from understanding this, and maybe Owen can pitch in, and I know Nicole is going to talk a little bit about this later, is that LOFAR observations can actually really help with this to measure the total electron content. So LOFAR for space weather will have this capability, I think. And you know, when we do it with GPS signals, when we try to measure this total electron content, we use two frequencies to measure this phase difference. However, if we look at the phase shifts of a signal passing through the ionosphere, we can see it's dependent on the total electron content and the frequency. So if you can observe kind of distant objects in the sky, or point sources in the sky, over a range of frequencies, you can essentially determine for really good accuracy what the total electron content is through that signal that's propagating. So it's used by LOFAR essentially to calibrate LOFAR data, because you don't want your source to be moving all over the place. So this is a lot of the work that's been done to try kind of correct for this ionospheric disturbance. But in a way, we can actually get information back out about the ionosphere by correcting for it. So this is really interesting, and this is some nice simulations that were done between core stations and remote stations, and making essentially a map of the vertical total electron content over space, which is really nice. And this is a simulation for looking at data with LOFAR 2.0. So I think an awful lot can be done with LOFAR, particularly to look at the ionosphere. And I know other kind of work has been done in that way. And I tried to do a literature search to see if this has really been done, you know, during the day and maybe during a large solar flare or anything like that. And from what I can see, that has not been done yet. It's still kind of early days, but I think there's an awful lot of potential there to kind of go forward and use LOFAR as a space weather instrument to really look at the ionosphere and probe the ionosphere. I think it's really interesting. So maybe we can talk about a little bit about that more at the end, because I'm not like, maybe some people know a lot more about this than I would. So just in terms of looking at the total electron content during a flare, this is some nice work that was done looking at large flare in 2003, looking at both GPS observations of the total electron content and then matching it with a model of the ionosphere to essentially get at what the electron density profile is, or this total electron content throughout the whole ionosphere. So this is looking at a pre-flare and during the flare peak. And if we look at this difference, we can see how much the total electron content changes over a flare. And I guess just something to note, if we're looking at the delta TEC, it increases by 4. That's not really actually that much. If we're talking about orders of magnitude increase in the D region, which I talked about. So while it does really affect these upper regions, it's not hugely dramatic. And this TEC unit is around 10 to 12 electrons per centimeter cubed. And similarly, this is for this X9 flare. So we can see it actually increased a lot more. So this is around up to like 22. I actually think I have those plots backwards. But yeah, so this is the September one, sorry, and this is the November one. But this one was much larger, so that makes more sense. This flare, the X23 flare, had a much larger increase in the total electron content. But just again, if we look at kind of different, a lot of work has been done in this, and this is where kind of the majority of research has been done in ionospheric physics and its comparisons with the output of the sun. We see that TEC really depends on the time of day, so the solar zenith angle on having an impact on the TEC. It also really depends on the location of the flare on the solar disk. And this goes back to kind of what Peter said about Lyman alpha. A lot of EUV lines are optically thick, particularly chromospheric emission. So those flares that occur kind of closer to the limb are going to have opacity effects, and essentially you're going to be reduced emission as it's absorbed in the solar atmosphere. So this is why we see this location of the flare on disk relationship for kind of higher up in the F regions. And I'll show that's actually quite different for the D region in a moment. And this is just some final plot to show, this is again this X23 flare, and this is a combination of observations and modeling to look at the increases or the electron density in relation to this flare. So this is the EUV flux. You can see it's fairly instantaneous across the whole ionosphere. But actually up where in the kind of higher F regions, we've seen that it doesn't really go back to normal for several hours later. And this again is due to the fact that you've very low neutral density, so it takes an awful lot of time for things to recombine. So this is just something to think about. It takes much longer higher up in the F region to kind of come back to its normal state following a flare. Now moving on, if we think again, as I described about magnetic crochet, so these are signatures of currents in the E region that are kind of increased by caused by increases of electron density in this E region. And they're seen, this is this recent X-class flare from essentially 2 weeks ago. They're seen in ground-based magnetometer data as these crochet signatures, and they've actually gotten their name, I think, from crochet means hook in French, apparently. But I think it's really from this crochet needle that has that hook-like signature, and that's where it got its name. It's also known as the solar flare effect. And we can see these as significant changes in the magnetometer data. And these again are just signatures of increasing the geomagnetic field essentially in the ionosphere, which is really interesting that you can have a flare having such a strong impact. And this is one of the ways we can really probe at the E region at understanding how solar flares affect that region. Now, these are really not fully understood in a sense of how common they are or when they occur to really cause this magnetometer crochet. And a lot more work needs to be done here. And really is only seen in some studies for large events. And the question is, why is it only seen for large events? So what we've seen so far is how we can kind of probe at the F region and the E region. But going back, I did mention before, the D region is probably the one that we really need to care about the most in relation to space weather effects into solar flares. And again, why we care so much is that, as I said, the X-rays dominate ionizing this region during a flare. And if essentially then what happens is any radio waves that are propagating through it get attenuated or absorbed. And this is a nice kind of figure just to highlight that. This is if we look at, say, 5 megahertz during a flare and we look at the signal strength, it can significantly decrease and sometimes be completely, you just can't receive it during a flare. So it's really the D region that has this largest impact during a flare. So again, just going back to this idea of the D region absorption model, and we can see that it can, this red is that you can't essentially use high frequency radio communications in this region at all during a flare. Now, a little bit going back about the D region, it's formed, as I said, during the day, caused by Lyman alpha line. And this is the strongest line that we see from the sun. But again, the X-rays dominate to N2 and O2, is the dominant particles. And again, as I mentioned before, it is too high for balloons and too low for satellites. So we really need ways to remotely sense the D region. And this can be done essentially through the observations of the propagation of very low frequency radio waves that propagate within the waveguide formed between the Earth and the ionospheric D region. So here, very low frequency in this term actually means 3 to 30 kilohertz. So at these frequencies, the D region is actually quite a sharp reflective boundary. So during the day, this propagation is quite stable both in amplitude and phase. But when a solar flare occurs, we're going to have a significant increase in this electron density profile. And it's going to have significant changes of this upper waveguide boundary. And in this way, these changes are reflected in the amplitude and phase measurements of any VLF radio wave that's propagating from a transmitter to a receiver. And going back to the idea that there's an awful lot of, huge transmitters located around the world that are used at these frequencies to communicate with like submarines. And they use very large power transmitters, so up to 1 megawatt. And these are continuously transmitting frequencies in this range. And what we can do is we can set up little receivers to pick up these different frequencies, only the amplitude and phase, and monitor different paths over the ionosphere to see how it's going to change in respect to a solar flare. And really, when we look at these amplitude and phase measurements, we get an idea, and we can use these together with theoretical models of the electron density in the D region to kind of get at to quantify what this electron density is, and particularly also look at the collisional frequency. Just to give you an idea of what this might look like, these are some observations from a receiver we have in Birr in the middle of Ireland. And this is picking up from a transmitter in Maine in the US. So we're probing the ionosphere essentially across this path. And this is what the VLF amplitude looks like. So we can see there's this rise, this large dips at the sunrise and sunset, and that's due to do with kind of modal components and an awful lot of complicated physics, terminator physics going on that we don't really care about. But we can see that during the day, it follows this nice diurnal pattern. And this is actually what a day looks like when there's no flares, when the sun isn't very active and everything is quite stable. However, when a solar flare occurs, this is going to, again, increase this electron density profile of the upper waveguide. It's going to give it a sharper reflectance, essentially, so waves at these frequencies are going to be less attenuated. And this is why we see these amplitude increases of flares during this time. And essentially, if we compare this then to the X-ray flux that we see from GOES, we can see that we're really using the D region as a giant X-ray detector, and it's able to see these flares very nicely. And in this way, this is one of the only ways we can really observe and identify solar flares in this D region and be able to probe kind of how they affect this region and how we can understand its geophysical impacts. And
Nora,
this is
can I just ask about that previous plot? That's a really nice plot. So there's an M1 at the start of the day, and it has such a big response or whatever, and then the M something at the end of the day has a smaller response. So is it the case that it's more complicated than the bigger flare? A big flare will cause such a big response. It obviously varies between classes as well.
Yeah, that's a really good question, and something I'm going to try to highlight. This really also depends on the background conditions of the ionosphere. It's also going to depend on the time of the day. So you can see flares that usually occur at 12 o'clock or when the sun is at solar zenith have a larger effect. It's also this idea that the GOES class isn't a very good reflectant all the time of the spectral components of the flare. So we don't know those two M1 flares, like maybe one had a very hard X-ray spectral component that we aren't seeing. So just care needs to be taken, and we don't necessarily see a full linear relationship between the GOES class and these fluxes.
Generally, one could expect if there was an X-class flare, it would be a bigger response than all of these.
Yeah, exactly.
Yeah.
Yeah, that's a really good point. And yeah,
just on that, Owen, there's it's almost a linear relationship if you plot. There's some scatter plots that show, you know, almost a linear relationship between the ionospheric response and the X-ray GOES class.
Yeah.
But that's what I was thinking. Yeah, with a bit of scatter about the linear.
Yeah. And it's coming right up, so you're in for a treat.
But sorry, Laura, can I ask another question? But has this been corrected for I don't know, the position of the sun in the sky? Because it seems like there could be like a general effect, but I guess not. Oh, but that's that tiny little change.
Yeah, that's a good point.
In the quiet time. Okay.
This plot hasn't, just because it's the raw data, but you can see, like, you know, even in the gray curve, you can see the position of the sun in the sky almost in it, right? So this is when the sun is almost directly overhead. So this is when we're doing these type of studies, we need to be careful about background subtracting the pre-flare, essentially, conditions of the ionosphere to make sure you're comparing them correctly. And, you know, especially when a flare happens around the terminators, you know, it can be really low signature because there's just an awful lot of other chemistry going on.
This is Nicole. If I can ask a question.
Yeah.
Do we have any idea of the exact photon energy range which makes this ionization?
So no, I think there's so much work that needs to be done on this. I think what people usually would say is that, you know, the 1 to 8 angstrom channel works really well. It's less than 10 angstrom. But it really depends on both, as you said, the spectral components, but that's different compared to the different heights. So you find that, say, harder X-rays actually penetrate down lower in the ionosphere than higher up in the ionosphere. And what we're doing here is we're really probing kind of a range of the ionosphere. So these really need to be combined with theoretical models to understand, you know, what parts are really impacting this D region. So we know that, say, it's X-rays lower than 10 angstrom that are impacting the D region, but we need to do full spectral analysis to really understand how they are impacting, because I don't think we have a really good handle on that yet. Especially with this type of measurement, it's challenging to see.
Okay, thank you.
Thanks.
There's also another question from Peter Petkov there.
Yeah.
Yes, thank you. Do you guys have tried to monitor the phase of the signal, not only the amplitude? And do you think it will bring some useful information to these observations?
Yeah, that's another really good point. We unfortunately don't have phase measurements at the moment, but phase measurements are really, really important, particularly when we're using them together with theoretical models to understand how do we go from BLF signal amplitude to an actual electron density measurement. And we can do that by using the long waveguide propagation capability code, which essentially models the ionosphere or the lower ionosphere as a waveguide. And to do that, you really need both measurements to be able to constrain that model. But what you would see if we did a phase measurement would look quite similar to this. And one other thing is I'll show in a plot later that we started to see that the amplitude actually saturates at a point. So when you get kind of to larger X-class flares, the increase in amplitude can saturate, where that does not happen with phase observations. So it's really important to also have phase observations. Unfortunately, at the moment we don't, but other observatories do. And it's something we've been thinking about for sure. Because there has been some work to show that the phase observations are actually much more linearly dependent on the GOES X-ray observations. So you can essentially really calibrate those observations to kind of use the ionosphere as a giant X-ray detector. So yeah, we wish we had phase observations, and they would definitely help.
Great, thank you. Thank you very much.
Yeah, I'll mention a bit more in the end. This is just to highlight again kind of how sensitive you can really use these observations to get at different features of solar flares. So this is some work I did, and this is how I kind of got into looking at the ionosphere, was study pulsations in X-ray emission from flares. And the question was, well, we know X-ray emission impacts the lower ionosphere, can we detect these pulsations? And we found that in this one case of a very strange loop that was oscillating with a period of around 20 minutes during this region, we can find that they actually have a significant impact in the Earth's ionosphere, essentially driving the electron density variations based on this quasi-periodic pulsations. And if we look at the D-region absorption model over the ionosphere at this time, so this was the region of the ionosphere we were probing, you can see that the ionosphere is essentially pulsing in response to the solar flare pulsations, which is really, really nice. So just again to highlight, case studies are really important, going back and looking at these events and to try to understand, this direct relationship between, what's happening on one flaring loop on the sun and how it's impacting us here on Earth. And I think this goes back to your question, Owen. This is a recent statistical study we've done with our measurements over the past solar cycle. We have around 300 flares, and we looked at, the VLF amplitude increases compared to the GOES channels. And what we find is if we plot the VLF amplitude excess, so this is taking into consideration, the background of the time of the day and the season, of course, is an effect as well. So when we take that all into account, we can see that there is this nice linear increase. Unfortunately, we only had 2 X-class flares. So it's hard to see if there is a turnover here or whether these are just outliers. But you can see this nice linear relationship, and it has a strong correlation coefficient. But again, going back to...
Sorry to interrupt, maybe is that to do with the saturation effect that you said happens? Yeah,
we think that could be, but we're not entirely sure with those two flares whether that was just a strange coincidence or not. So we definitely need to...
Very nice plot.
Yeah, no, it's nice. And as kind of Nicole goes back to the question of like, if it is just the GOES 1 to 8 angstrom channel, if that's where, the spectral component that has the strongest effect lies, why is there so much scatter here? You should expect it to be kind of much more linear. So there is probably other things going on here and something to think about.
As well, surely the time of the burst with relation to the path of the VLF signal is going to make a difference as well. Like it's not as simple as just, it's linearly related. It might be linearly related, but the path of the VLF signal is going to be different, which kind of gets back to what Cameron was saying about, it's not just so simple, I guess.
Yeah, no, absolutely. It's a complex system between, the whole solar terrestrial relationship. But it'd be interesting. I wonder if we looked at, say, other wavelengths here, would we get down to kind of bringing in that line some more? Because we've tried to take into account, choosing flares that were quite similar in time and taking away a background to make sure that, we take out seasonality effects and things like that. But yeah, that's a good point.
I'm sorry, how big are the error bars on this plot, do you think?
That's a good question. I should probably put some error bars on. They're not huge. They wouldn't be super large. Just based on like having a look at the data, they wouldn't be significant. You wouldn't see like a large line here, for example.
It's a nice power law relationship.
It's a lovely plot, but if you think about trying to make a prediction based on, say, the X-ray flux, you get a lot of different answers on the left-hand side. But I think there's a good argument for dropping lots of receivers around the Earth, as many as you possibly can, and then that would help you to deal with Shane's point about propagation effects, or Cameron's point about correcting for position of the sun in the sky, which are things that so it's a way of setting up a monitoring system and then correcting for those effects, and then calibrating basically the ionosphere to act like a big X-ray ray detector.
Yeah, no, absolutely. And I think that's one of the takeaways from the statistical study that we performed that we're going to try publish is, this is really cool and we should be doing more of it. We should set up these cheap detectors around the world, and there's a lot of science that can be gained, and we're really only scratching the surface with these type of simple plots. So I think there's a huge wealth of information, as I mentioned.
And there was a paper, just to get back to Peter's comments there as well. There was a paper published quite recently looking at the solar flare impacts, and the phase can be very useful in looking at the ionospheric response. So phase and amplitude are both useful.
Yeah, absolutely. So I'll just finish up here with 2 more slides. So this is just going back to look at, with the same statistical study, you know, looking at the location of the flare and disk and seeing if that has an impact again on how the excess VLF amplitude is going to fare. And we find that, you know, we really don't see any relationship here between, you know, heliographic angle and VLF amplitude excess. So if we looked at kind of the F region, for example, you would see actually like a turnover here, because as you go closer to the limbs, you have this opacity effects of the EUV emission. But of course, this makes sense in terms of X-ray emission, because X-ray emission is optically thin. So we're going to see that there isn't going to be a center to limb variation with X-ray emission. So it really doesn't matter if the flare is occurring on the limb or on the center of the disc. So just kind of another takeaway and another difference between the D region and the upper region. And just a final point is, you know, this again goes back to Nicole's point, you know, not all flares are created equal. And a lot of work has been done really only using the GOES classification or the GOES fluxes to compare different flares with each other. And that's not necessarily the case. So this is an example where we have 2 flares that occurred on the same day with similar GOES magnitude. If we look at the Lyman alpha emission or the chromospheric emission, we can see the first flare had a very, very small signature in Lyman alpha, but the second flare had a very large signature in Lyman alpha. If we go down and then look in the E region, we can see, you know, there's no signature in the E region of this first flare, even though it had, you know, a similar GOES magnitude. But we see this nice crochet in the second flare, and maybe this is due to the fact that we have more chromospheric emission, it's impacting the E region some more. And then when we go down to the D region, we can see it nicely closely matches the GOES X-ray emission. So again, it's highlighting that X-ray emissions are the lower regions. As you go up in the atmosphere, we need to really start thinking about how these different lines, how the spectral components of different flares are essentially impacting the ionosphere. And that's really something that has to be done, and it has not really been done too much yet. So again, what needs to be done and where we need to go is look at kind of detailed spectral analysis of flares, both in the X-ray regime and the EUV regime, and try to identify this ionospheric response through the whole ionosphere. At the moment, we're really looking at it in different sections, but you know, we really need to look at it as a whole system. And I think even just to start off is, you know, do further statistical studies of VLF and magnetometer data. A lot of times, you know, you have observatories that have co-located VLF and magnetometer data. So we should be able to first off have a look at, you know, how is the E region and the D region affected together, and what are the spectral components that really matter there for driving these geophysical impacts. And just a final note again, you know, it isn't just on Earth that we have an ionosphere. Other planets have an ionosphere, and all planetary atmospheres and ionospheres are impacted by solar flares. And one that has really come to light in the past few years is Mars, because Mars is actually quite a similar structure ionosphere to Earth. And it's been seen in several different studies that, you know, flares significantly impact the Martian ionosphere. And similarly, it significantly impacts the lowest region of the Martian ionosphere. So this is an example of a large flare looking with some data, and we can see it's the lowest region similar to the D region on Earth, so the D region on Mars. I don't think it's actually called that, but you can see that that's where you have the most significant increase. And then similarly, MAVEN has been really rudimentary in looking at this, and similarly for these September flares that we talked about before, we can see it also had a significant increase on the lowest lying region of the Martian ionosphere. So I think even more work can be done if we, you know, probe together flares that were observed on Earth and at Mars, and, you know, compare the atmospheric response or the ionospheric responses. It might also help us understand a little bit more about the Martian ionosphere. And similarly, if we're going to send someone to Mars, radio communications are important if they're on the ground, and they're going to have the same problems that we have here. They're going to need to be able to mitigate ionospheric impacts and radio signal communications, et cetera, et cetera. So, you know, looking ahead, what do we really need to do? I try to highlight here, we really need to communities really need to talk together more. And this is some of the problems, the ionosphere community and the solar community, even though those two fields are so related, we don't talk together to each other enough. And similarly, the data sets that we both have are both very rich, and if they can be pulled together, we can really see some new results, I think, over the next solar cycle. In terms of new prospects, I think there's lots of new solar instruments that are up now that are taking detailed spectra from the sun, so we can use those together with a combination of lots of different ground-based observations that are looking at the ionosphere from the D region all the way up to the F region. And I think we really need to look at that again as a whole system body and try to understand how different spectral components of the flare, how do they affect the different regions of the ionosphere individually? And this is kind of a point that I'll leave here. Maybe we can talk about, because I don't really think I know enough about that LOFAR 2.0 and LOFAR for space weather and other kind of techniques used by SuperDARN, for example. These provide a way to kind of probe the ionosphere in kind of really neat new ways. And from what I can tell, and someone can of course correct me, I don't think they have really looked at daytime ionosphere yet, or when there's been a solar event. And I think this is going to be really interesting going forward, and there's going to be so much data available. And how do we utilize that data essentially properly going forward, and to be able to understand the ionosphere to new ways. So I think if anything, we have too much data coming online. We need to have scientists working together and smart techniques and software to be able to analyze this and to really make new discoveries about the Earth's ionosphere and its relationship to the whole solar terrestrial environment. So just to summarize here, the ionosphere is an ionized portion of the Earth's atmosphere, and it's really important for all radio wave propagation, whether you're looking at communications, whether you're looking at observing distant planets or the sun. You really need to take into consideration the ionosphere. Solar flares have a really significantly direct impact on the ionosphere. This is particularly apparent in the lowest lying regions, so particularly the D regions. And being able to analyze solar flare effects can really help us understand, space weather, and also help us to kind of probe down to the complicated physics and dynamics that are occurring in these ionospheric regions. And again, so much more work I think needs to be done, and we really need to kind of utilize the data properly and work together between different communities to get a better understanding. So thanks very much. That's all I had to say. So happy.
Thank you, Laura. That was really excellent talk. Some fascinating stuff in there, and I'm looking forward to seeing the published stuff from that small antenna. I'm so amazed that the small antenna can do so much. It's amazing. It's just so good.
It's actually great. It's
that's Carmen clapping you. Not a question, I think. Is there any questions for Laura in the last few minutes? Yeah, Mohammed?
Yes, thank you very much. I have a question about the magnetic crochet signal. The electric current produced by the solar flares in the E region, is it always produce the magnetic field in the same direction as the magnetic field of the Earth? So that's why we see a little increase in the BZ component, or something different?
Yeah, that's a great question. And it's actually something I fully don't get my head around. And I think it also depends on where you are on Earth. But yeah, it's to do with the direction of the magnetic field. I don't know if anybody online has a better description of that. Peter, maybe you might know.
Yeah, I mean, the particles drift down along the magnetic field, but then there's a drift that then gets them to go from east to west, right?
Yeah.
Sorry, I shouldn't say right, but from east to west. So that's the primary direction of the current in the northern hemisphere, and then that itself creates, through the Faraday effect, a magnetic field about it, which also has the same orientation, always in the northern hemisphere and always and similarly in the southern hemisphere, and then that couples to what I consider to be the background kind of dipolar magnetic field of the Earth, and then affects your BX, BY, BZ. But there's a downward component and an upward component that affects your BZ and adds to your BZ. That makes sense.
Yeah, thank you very much.
One last question, if there is, before we break.
I have hopefully a quick one. Thanks, Laura. That was really, really great. I was going to ask about the time delays between when we observe the flare and the response in the ionosphere. Yeah, like, is that just literally the chemistry of ionization, or is there more to it? Do you know?
Yeah, no, that's a really good question, Piers. And so yeah, so there is a time delay between, as you said, like the peak in the X-ray flux and then the peak we see in the response. And this isn't due to anything to do with like light travel time or anything, which if it was light travel time, it would be less than a second. It's essentially to do with, in the D region itself, as I kind of mentioned, is that, you know, recombination dominates. So when you have ionization, it takes kind of a while for this continuity equation of, you know, the photoionization and the recombination components to kind of get to a balance. And essentially what you find is that the photoionization, you know, kicks out the recombination for a little bit longer, usually around a minute or two after the flare, before the recombination dominates again, and you see that peak turnover. And it's to do with like a really complicated chemistry in the D region. Essentially, it's eventually a balance between the photoionization and the recombination. And it also depends on the time delay, depends on, again, going back to this idea of, you know, what spectral component is the most dominant. And we find that when you go, the time delay is less for higher energy X-rays. So if you look at, say, the higher channel of GOES at the 0.5 to 4 angstrom, we find less of a delay. So I think there's an awful lot to be done there, but that time delay can actually be used to make estimates of the effective recombination coefficient. So this is a coefficient that embodies, say, all the different recombination processes that occur. So it holds a lot of physics. But yeah, as you said, it is just to do with the recombination.